It is 7:45 a.m. Somewhere in a large city, a water pipe is about to burst. No alarm has gone off. No engineer has been called. No citizen has complained. But the city already knows. Sensors in the water network detect a subtle pressure change. The city's AI predicts the pipe will fail within minutes. A repair crew is already on its way. 3 blocks away, traffic lights are silently reconfiguring themselves. Because the city's AI has detected an unusual cloud forming in a swoop, an ambulance is being rerouted to a nearby street, not because an emergency call came in, but because the system has predicted one is likely. None of this is science fiction. This is what happens when an entire city runs as a living, breathing digital copy of itself, updated continuously, thinking autonomously, acting in real time. This is a real-time digital twin of a city. And as we will see in this chapter, it only becomes fully possible because of 6G. A digital twin is a virtual replica of a physical system. It continuously receives data from the real world through sensors, cameras, vehicles, and infrastructure, and updates a digital model in real time. This virtual model can then simulate scenarios, predict problems, optimize operations, and even trigger automated responses. In other words, the digital twin becomes a living mirror of reality. The concept didn't appear overnight. In the 2000s, early versions were used in aerospace. Organizations like NASA created digital models of spacecraft systems to simulate failures and plan missions. In the 2010s, the technology moved into manufacturing. General Electric pioneered the use of digital twins to monitor jet engines in real time, tracking wear, predicting maintenance lists, and preventing failures before they happened. By the 2020s, the 5G era, the ambition scaled up to cities. Singapore launched its Virtual Singapore project. Helsinki built a detailed 3D digital twin of its urban environment. These were remarkable achievements, but they were limited, partially real-time at best, dependent on separate sensor levels, unable to act autonomously. The 2030s, the 6G era, is when this changes fundamentally. Every building, every road, every vehicle, every pipe will learn continuously at millisecond resolution, but a level intelligent enough to not just observe the city, but to manage it. Think of Google Maps, but instead of showing you where roads exist, it shows you the real-time state of every piece of infrastructure in a city. And instead of just showing you, it is constantly making decisions, optimizing traffic, energy, emergency response, and air quality, all simultaneously. A fully operational 6G-enabled city digital twin doesn't manage one thing. It manages multiple interconnected city systems simultaneously. A city digital twin can track traffic patterns using data from vehicles, road sensors, and cameras. The AI doesn't just react to congestion, it predicts it 15 to 20 minutes ahead and preemptively reroutes traffic before the jam ever forms. Emergency vehicles receive an automatic green corridor, every traffic light on their route clearing ahead of them without a single human instruction. Studies suggest a well-implemented system like this could reduce average urban commute times by an estimated 20 to 30%. In a city of a million people, That is hundreds of millions of hours returned to human beings every year. The tree monitors the energy consumption of every building in real time. But more importantly, it predicts demand. For example, when a football match ends or during a heat wave, and adjusts energy distribution. This kind of optimization could reduce urban energy waste by tens of percent. Thousands of microsensors embedded in bridges, tunnels, roads, and skyscrapers continuously feed data into the train. The AI analyzes micro vibrations, stress fractures, and material fatigue patterns invisible to any human inspector. In August 2018, the Morandi Bridge in Genoa, Italy, collapsed without warning. 43 people died. Subsequent investigations found that the structural deterioration had been developing for years. With a 6G-enabled digital twin, the AI would have detected those structural abnormalities weeks or months in advance and fettered them for intervention long before any lives were at risk. That is not a hypothetical benefit. That is a human life saved by data. Digital twins can map pollution levels across a city in real time. By combining sensor data with weather models, AI can predict where pollution will move and adjust traffic or industrial activity to reduce exposure near schools or hospitals. When a disaster occurs, a fire, a flood, an earthquake, the train immediately begins simulating the event. It models how a fire spreads through a building. It calculates optimal evacuation routes in real time as conditions change. Critically, during an active building fire, the train can provide first responders with a live interior map, showing exactly where people are located inside, not based on floor plan alone, based on live sensor data. Pressure sensors distributed throughout the entire water network detect leaks within seconds of them developing, not days later when a sinkhole appears in the road. Smart waste bins across the city zero their fuel levels continuously. Collection vehicles are dynamically routed only to bins that actually need emptying. No more half-empty trucks making unnecessary rounds. Fuel saved, emissions reduced, cost cut. To do all this simultaneously, a real-time city digital twin must continuously process data from an extraordinary range of sources. Millions of IoT sensors, connected vehicles, drones, cameras, infrastructure monitors, and live weather systems, all fitting into a single unified model all the time. The network carrying all of this must handle massive continuous data flows, run non-stop AI analysis, and enable instant decision-making, not occasionally, not on demand, but every single second of every single day. A city's digital twin may need to process millions of data updates per second, and that is precisely where 5G runs into a wall. 5G is a major technological leap, but it still faces several limits. First, there is the data volume problem. A city-scale digital twin produces enormous sensor data streams. 5G networks were designed mainly for human-focused services, like video streaming and mobile apps. Handling continuous machine-to-machine data at city scale pushes beyond its original design goals. Second, there is latency. For a digital twin to respond instantly to events, like a pedestrian stepping into traffic. The cycle from sensor to network to AI processing and back must happen extremely quickly. Real-world 5G networks typically deliver 5 to 20 milliseconds of end-to-end latency. That is excellent for streaming video, but large automated systems often need even faster response times. Third is the intelligence gap. Most AI processing today still happens in distant cloud data centers. That means sensor data must travel across the network, be analyzed, and then return with instructions. This round-trip delay becomes a bottleneck when decisions must be made instantly. Finally, there is device density. 5G networks support roughly 1 million devices per square kilometer. That sounds huge, but a fully instrumented smart city could eventually involve tens of millions of sensors in the same area. This is where 6G technology becomes transformative. Future 6G systems aims to provide terabit-level data speeds, opening bandwidth far beyond today's levels. Latency could drop towards sub-millisecond levels, enabling extremely fast response times. But perhaps the biggest change is that AI becomes part of the network itself. Instead of sending all data to distant cloud servers, intelligent processing happens at the network edge, close to where the data is generated. In effect, the network becomes part of the city's nervous system. Another major breakthrough is something called integrated sensing and communication. In current networks, sensing and communication are separate systems: cameras, radars, and sensors. In future 6G systems, radio signals themselves can also act as sensors. This allows network infrastructure to detect movement and map environment while simultaneously transmitting data. It means the city can sense itself through the network. Elements of this vision are already being built. Singapore's Virtual Singapore project is one of the most advanced urban digital twin platforms. Helsinki has developed a detailed 3D city model used for planning and climate analysis. Cities like Zurich, Shenzhen, and Shanghai are also experimenting with large-scale digital twin systems. And Europe's Destination Earth initiative aims to create a digital twin of the entire planet to support climate prediction. The question is no longer whether digital twins will exist. They already do, just in early forms. The real transformation will happen when future networks make them fully real-time, autonomous, and intelligent. Everything we have discussed today, the traffic, the energy grid, the bridges, the emergency response, all of it applies not just to cities. Digital twin technology is expanding into manufacturing, healthcare, energy infrastructure, and aerospace. The same principles that allow a city to mirror itself in real time can allow a hospital to mirror its patient population, a power grid to mirror its entire distribution network, or an aircraft to mirror every component of its own structure in flight. Digital twins are not a single application. They are a new way of understanding and managing the physical world. And 6G is the infrastructure that makes that vision real at scale. We will further explore another revolutionary application that AI-native 6G could unlock, one where thousands of machines don't just connect, they think and act together. Welcome to the world of robot swarms.